Okay, so in the last class we discussed the axioms of probability, okay, their properties, and then we discussed something called field of sets, okay, and in that connection we mentioned Boreal set, Boreal field. Okay. I will just touch upon those things today to start with, and also explain the motivation for considering these, but this is again only for mathematical correctness. But having just done that, I will move on to the notion of conditional probability, okay, that I will be explaining first notionally and through examples. Then using this conditional probability, I will find out its properties. Then we will discuss something called total probability and Bayes theorem. Again we will take up some examples, and then we will go for statistical independence of two events, and we will of course try to give physical interpretation of these. Okay. So, as I mentioned in the last class, I will consider a field, of sets F. It will consist of suppose sets S1, S2 and dot 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 so on and so forth. Okay. Now, this will be a field if for any S I would say element, because this is a field means it is a class of sets. So, each set is an element of this class. Okay. If we should have S I bar also member of F. That is, if a set belongs to this field, then its complement also must belong to the field, number 1. And number 2 is if A is an element of F and B is an element of F, then their union also is an element of F. These two conditions must be satisfied. There are some properties which follow this, which we will be now considering. Sorry. Okay. First, let us consider this thing, that suppose A is element of F, B element of F, then we will show that their intersection A B, it is also an element of F. It is not very difficult to show. Well, we can always write A B as using De Morgan's law. Okay. Now, we know that if A is an element of F, then A bar is an element of F. Similarly, B bar is an element of F, and since this is an element of F, this is an element of F, their union is an element of F, and complement of that union also is then an element of F, which means this is an element of F. Okay. Another interesting observation is that this field consists of both the total set S and the empty set phi, because total set S is nothing but S is A plus A bar, and A is non-empty because the field F was defined to be a non-empty class, which means there has to be at least one non-empty set, say A, and therefore its complement when put under union they give rise to S. Okay. And since A is a member of F, A bar is a member of F and their union is a member of F, this means that S also is a member of F. Okay. Similarly, empty set phi can be written as A bar, and once again A is a non-empty set because there is at least one non-empty set A member of F, and A bar, there is the intersection between A and its complement is empty set, and since both A and A bar are member of F, their intersection also is member of F. Okay. So, these are the properties of a field of sets. Next, we consider what is called Boreal field. The Boreal field F, it is such, it implies that if you take any sequence of sets and you see the sequence consists of infinite elements, each is a set, then not only A1, A2, A3 and other members of the sequence are member of F, but their union intersections. For instance, A1 union A2 intersection A3 union A4 and so on and so forth. Any finite or infinite union or intersections, they are also member of F. Okay. This is called a Boreal field. Why we are doing this is because so far when we have defined these probability axioms, we have considered basically finite sets, and we said that the set consists of, the set actually is a total event, it consists of experimental outcomes, and we formed various subsets using those outcomes and we call them events. But when you are dealing with infinite sets, then all possible subsets really do not qualify for events, because these probability axioms cannot be applied to all the subsets, there will be some mathematical difficulty. Then we say that in such cases, those subsets which form a Boreal field, they would qualify for events, and these probability axioms can be applied there. For example, we know that if we have some events, say total k events A1, A2, Ak, and k is finite and they are mutually exclusive, then obviously we can write this as summation of the individual probabilities. Question is, if it is an infinite union, okay, can we write like this? So, mathematically we cannot just jump at this this fact that this statement that okay we can write. Actually, for that to happen, A1, A2, A3 and other members must form or must come from a Boreal field. Okay. Then we should be able to write it is an infinite sum, all right. So, this we are discussing just to remain mathematically correct. Okay. For that purpose only I introduced you to the concept of field of sets and then Boreal field, so that our definition of this basic axioms, they are more complete and more correct. Okay. So, that is all as far as these axioms are concerned. We now move to a very interesting topic, that is called conditional probability. Conditional probability means that suppose we are dealing with total event S as before, that is S is the total event, okay, S is the total event, and M an event, basically it is a subset of S, okay, and A is another event. Again subset of S. First I give a definition, then we will come to its physical interpretation. Conditional probability, we write like this: P of A given M is defined as P A M, that is a joint probability, okay, that is the probability of the intersection between A and M that occurring, okay, the event being the intersection between A and M, that probability of that event divided by P m. Actually, by this conditional probability, what we are trying to say is this, that look, P of A means probability of the event A occurring. That is, if event A has various possibilities, that is various elements forming the subset, then for any of these element occurring or being true is given by P of A. P of A by M means that suppose we already know that an event M has taken place, then subject to that knowledge, what is the probability that event A also has taken place. Okay. Now, how that comes from this definition and all, we will see soon. Okay. But certain things follow from here. Firstly, suppose it is given that this set A is nothing but a subset of M, that is, the event A is already contained in event M. In that case, we know P A M, what is the intersection between A and M? Intersection between A and M is A itself. So, this is equal to P A. Okay. In that case, is P A by P M, which is surely less than equal to P A, because P M is what? It is non, I mean, I am assuming that P M is non-zero. Okay. So, this division is allowed, all right. It should be, it should be greater than equal to. That is, P m is less than 1, obviously P a by P m is greater than equal to P a. When P m is 1, then only it is equal to, otherwise it is greater than P a. And I am of course assuming that P m is non-zero, okay, otherwise this division is not allowed. It means that if we are considering the occurrence of the total set, total event, which is bound to occur always, and subject to that we see the probability of A, then of course probability of A is less, because I am really considering all possible events, and in the background of that I am trying to tell you something about the probability of A. But when I am not considering the total event S, but I am only considering the event M, and subject to the occurrence of event M, then I am trying to tell you the probability of occurrence of A. Obviously, chances will be more, because since I am restricting myself to M first, I am basically not considering all other possibilities. As a result, chance of observing A higher. All right. And other thing is, secondly, if M is contained in A, this event M is basically a subset of event A, which means P we had this, but intersection between A and M in that case is M, and this is P m by P m, which is 1. And obviously, if M is contained in A, then the fact that M has occurred itself means A has occurred. So, obviously, the probability is 1. Okay. See, what we are trying to do, we first enforce some definition and finding out some properties and trying to correlate those properties with some physical observation, okay, physical facts of life. But still a better interpretation will come up if we consider the frequency interpretation. That is, suppose you are conducting an experiment and suppose you are conducting an experiment and event total number of trial is n, or first let me write down n is the total number of trials, that is you are conducting an experiment, total number of times you conducted is small n. N A, and of course, small n is very large, N A total number of occurrence of event A. Similarly, N M same as this, but of event M. Okay. And N A M is the number of occurrence of A M, that is the intersection between A and M. Okay. In that case, if we apply our formula, then P A by M is P A M, there is the probability of the joint occurrence, there is the intersection between A and M, divided by P M, and what happens is N A M. What is P A M? We are having total trial small n, out of which N A M times we are getting this intersection. Okay. That is both A and M simultaneously. That means the corresponding probability, I put an approximate sign here, because once I get into the frequency based interpretation, I have to have some approximation, and approximation becomes better and better if total number of trials is larger and larger. Okay. So, this is divided by n, this is the probability standing for P A M, divided by, and what is P capital M? Again divided by n, out of n trials I got n M times this event M occurring, which leads to this. And try to understand the physical meaning of this. What it means, that though it is okay that we are conducting experiment and we are having a total very large number of trials called small n, but then we are not, as far as this result is concerned, we are now not looking at all the n trials, we are confining ourselves to only those trials where the event M had occurred. And how many such trials we have? N M. Out of these N M trials, on how many occasions did we have A occurring? Obviously, I have to see the intersection between A and M, because that is when both A and M occurs, and that is N A M. So, what is this giving? This gives you the conditional probability of the event A occurring subject to the fact that M has already occurred. I repeat again, N M is the, N was the total number of trial, but out of which if we just consider those occasions only where M has occurred, then total number of such cases is N M. So, out of these N M cases where on each occasion M has occurred, we find out on how many occasions A has occurred. For that you have to see the intersection between A and M and see how many times we really got this intersection, I mean this corresponding event coming up, that was this. So, what is the corresponding probability? That is total trial with M already occur, with M known to be occurring, divided by number of times A occurs with the fact that M has occurred. Okay. So, this is called conditional probability. So, it means that subject to the fact that M has occurred, what is the probability that A also occurs? This is this goes for P of A by M. This is a physical interpretation. Okay. Now, one can ask me this question that okay, I have defined one particular ratio as conditional probability, but still it is a probability. So, does it satisfy those basic axioms of probability for it to be acceptable as some sort of probability? Okay. So, we can take a look into that and see that these are also satisfied. Okay. First, P A by M, this was now both these probabilities are non-negative, and I am of course assuming that this is non-zero, because M is not an empty event. When we consider this conditional probability, we never put, I mean, the probability, the event here to be the impossible event. Okay, so this probability is not 0, but neither of them is negative, which means this is always greater than equal to 0. Okay. Of course, it will be 0 if this is 0, and this becomes 0 if A and M are such they are mutually exclusive. So, when A occurs, M does not occur, and vice versa, only then it is 0. So, this satisfies axiom number 1. Then, if S was the total event, how about P S by M? What is the probability of the total event? That is P S M divided by P M, and as I told you earlier, S intersection with M is M itself, because M is fully contained in S, because S is the total event, total set. Okay. That is S is a certain event, which means P M by P M, which is equal to 1. So, axiom number 2 also is satisfied. And now consider axiom number 3. Suppose A, B, there are two events, that is there are two subsets of the total event S, and they are mutually exclusive. A, B is phi. Then how about A union B? You can put a bracket around this, subject to M, condition to M. Now, we know, okay, first we will use the definition. This is nothing but A union B intersection with M divided by P of M. Okay. Now, we know, we have already seen the distributive property of these sets, I mean set operations, union and intersection. Okay. So, A union B intersection with M is nothing but A intersection with M union B intersection with M. Okay. And so, this leads to but A and B, they are mutually exclusive. So, A M, which is an intersection between A and M, so it is contained in A also, and B M, which is an intersection between B and M and is therefore a part of B also, they too are mutually exclusive, because A and B, they are mutually exclusive. Okay. Which means this probability can be written as okay, and PAM after all what is PAM by PM? That is by our definition of conditional probability, that is nothing but PA by M, and what is P B m by P m? Similarly, P B by m. So, again axiom number 3 is satisfied. So, this is indeed a probability, a notion of probability, which is called conditional probability. We now can consider some examples to have some further insight about this. Example 1. Suppose we consider this experiment, the fair die experiment. Fair means unbiased. Okay. It has got 6 faces. F1, F6. F1 means the face which is marked as 1, F2 is the face which is marked as 2, and so on and so forth up to F6. And since it is unbiased, I mean the probability of each face showing up is just 1 by 6. Okay. Suppose this is the case, and we are tossing this die. Okay. Question is, if we have given this, if we are given this event A, which is nothing but F2 coming up. Okay. Obviously, the probability of F2 as such is 1 by 6, given all possibilities, that is giving the total event, meaning one of the faces turning up always. Then, I mean in the background of that, the probability of A, event A, is nothing but 1 by 6. Okay. But suppose I consider another event M, which stands for even faces, either F2 or F4 or F6. That is faces which are marked as F2 or F4 or F6. Then, subject to the fact that M has occurred, that is, we are only considering those cases where the face that shows up on top, that is an even one. Subject to that, or under that circumstance, what is the probability that particular face is neither F4 nor F6, that is neither 4 nor 6, but F2. Okay. So, that will be by your formula, that is P of A by M will be P A M by P M. In this case, you see intersection between A and M, A is already a subset of M. So, intersection between A and M is nothing but A. So, P of A intersection M is nothing but P of A, which is 1 by 6, and P of M, you have got 1, 1, 1, 3 elements. So, probability of even faces turning up is nothing but 1 by 2, half for odd faces, half for even faces. So, it turns out to be 1 by 3. Okay. This is example number 1. But here one more example. Suppose a box contains three white balls W1, W2, W3 and 2 red balls R1, R2. we take out two balls at random. Okay. We take out two balls at random. What is the probability of first ball white and second ball red? Okay, what is the probability? This is a question. We can approach these problems in two ways. We can approach this problem directly using the basic axioms of probability. Okay. That is, we will consider all possible events, out of which we will find out on how many occasions an event like this will take place and take a ratio, and that will give us the solution. But there is one approach. We can also approach this problem in a smarter way using the notion of conditional probability. So, we will follow both. First, that is solution A, approach A. Here, first let us find out how many pairs we have. That is, pairs like W1, W2 is one pair, W2, W3 one pair, W1, W3 one pair, okay, and then W1, R1 one pair, and like that. So, total number of pairs is how many? 5C2. Okay. There are 5 elements, we are just combining, taking 2 at a time. So, that is equal to 5 into 4, 20. Okay. Out of these 20 events, each event is a possible pair. Okay. So, there are 20 events. Out of these 20 events, let us find out on how many occasions we can have first ball being white and second ball being red. That means, we can have combinations like either this W1 R1 or W1 R2 or again W1 R3. Similarly, for W2 R1, W2 R2, W2 R3 and W3 R1, W3 R2, W3 R3. Okay. Total number of such combinations, sorry, we do not have R3. I have to erase this. Sorry. Yeah. So, with W1, then either R1 or R2, then W2, again R1 or R2, and W3 again R1 or R2. Obviously, we have 6 combinations. Any of these combinations would give us a white ball first and red ball next. So, probability of this happening is then 6 by 20, because 20 is the total probability, total number of ways, total number of pairs, okay, out of which on 6 occasions we can get a pair like this. So, probability is 6 by 20. Okay. But using conditional probability, how to approach this? The solution B. That is, we use conditional probability. Okay. First, we find out P W by S. S means, here we are just taking one ball first. We are finding out on how, sorry, this is not P W by S, I have a better notation for it. Suppose we first find out that okay, when you take out the first ball, what is the probability of that ball turning out to be a white one? Okay. That is, we find out Pw. Okay. Pw. This will be how much? So, there are 5 balls, out of which and I am picking up any one at random. So, on 3 out of each 5 occasions, only on 3 occasions a white ball can come up. So, this is 3 by 5. Okay. And then after I have taken out one ball, which is a white one, okay, what is the probability that next ball is red? That is RW. Okay. That is, given that first ball is white, what is the probability that the next ball is red? Now, I have taken out one ball at random. It could have been red, could have been white, but suppose, of course, the probability of it turning out to be white is 3 by 5, but suppose it is now known to be white. That means, how many balls I am now left with? I am left with 4 balls. Out of these 4 balls, that is subject to the condition that the first one is white, it equivalently means that I am now left with 4 balls, out of which only 2 are white, not 3, and 2 are red as usual. Then what is the probability of next ball being red? That will be 2 by 4. In that case, what is the probability that first we have white followed by red? That will be, since conditional probability is joint probability divided by Pw, the other way I can write this joint probability is nothing but which is 6 by 20. That is the result we got earlier. Okay. We now come to something called total probability. Suppose S, that is the certain event, that is the total set, it has a partition in this form A1, A2 up to say A capital N. Okay. Means A1, A2 up to A n, they are subsets of S which are mutually exclusive and their union equals S. That is AI, AJ, this is phi if I not equal to j, and A1 sorry this is equal to S. That is a partition. Okay. That is, each is an event and they are mutually exclusive events. Okay. But union of these events is a total event, certain event or the total set S. Okay. Then question is, if B, a subset of S, is any event then P B, there is a probability of this event B can be written, and we will prove it, can be written as okay, we will prove it. This is called total probability theorem. Okay. It is very simple. We know that S is given by this. Okay. Okay, this is given by this. That means we can write B as nothing but B intersection S first. After all, B is a member of S, B is a subset of S. So, intersection between B and S is same as B, and then S I replaced by this. And using the distributive property of the set operations, we can write it simply as B A 1 plus B A 2 plus dot 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 B A n. Remember, since A 1, A 2 up to A n, they are mutually exclusive. So are these sets. After all, this is nothing but an intersection between B and A 1, which is contained in A 1. Then again B and A 2. This intersection is also a member of A 2, and similarly this is a member of A n, and since they are mutually exclusive, these sets also are mutually exclusive, which means P B is nothing but P of these, and since they are mutually exclusive, you can write like and then using the conditional probability theorem, I would say, or definition, we can write each of them like this. Okay. That means, if we know the probabilities of these events A 1 to A n, and in our statistics, these are called a priori probabilities, a priori okay. And if you know these conditional probabilities, that if A 1 has occurred, what is the probability of B occurring, and likewise, then using this summation we can compute the total probability of occurring of B. Okay, this is the total probability theorem. I mean, we extend this a little bit and we get what is an important theorem, which is called Bayes theorem. Okay. This takes us to Bayes theorem. For that, we see one thing, that we can write, say, B A I in two ways. Either you can write as before, that is conditional probability of B subject to the fact that A I has occurred multiplied by the probability of A I occurring. Okay. Alternatively, you can write like this. This is called a posterior probability, that if B has occurred, if that is known, then what is the probability that AI had occurred that could have triggered B. Okay. So, here we are looking, I mean we have already obtained the result B, and from there we are looking back and try to speculate what is the chance that AI must have occurred so that B has resulted now. So, this is called a posteriori probability. Now, we can write this a posteriori probability in this way then. That is, I take this below this, divided by PB, and PB is nothing but what we obtained last time for the total probability PB, that is let me say it is okay. This is called Bayes theorem, that is, given the a priori probabilities and the probabilities of the individual events, okay, we can find out the corresponding a posteriori probability. This is called Bayes theorem. I will give a problem based on this, but that I will not solve now, I will solve it in the next class. We have four boxes. Okay. B1, it contains 2000 items with 5% defective items. Okay. B2 contains 500 items and 40% defective. B3, it contains 1000 items. B3 before both, B3 before both 1000 items and 10% defective. We select one box at random. So, whether we pick up B1 or B2 or B3 or B4, probability of that probability of a particular box being selected is 1 by 4, that is obvious. So, we select one box at random and remove one component at random from the box. question, what is the probability that the selected item is defective? I would suggest that you all try this, and I will take up this problem in the next class. Okay. I now quickly move over to a very important topic. I will just touch upon, given the paucity of time now. It is called independent events. Two events A and B are called, in fact we call them statistically independent, if the probability of this intersection, which we call joint probability, because in this case both A and B have to occur jointly. So, joint probability is same as product of the individual probabilities. This is a very, very important concept. In the next class I will take it up. So, just to sum up what we did today, we continued with this notion of field of sets, and then Boreal field, and just explain why we need those concepts, basically for mathematical correctness. Okay. For those who are more interested in the axioms of probability and the probability theory, they can pick up from there. Then we moved over to a very useful concept called conditional probability. We examined its properties, then we gave some examples to throw further lights on it. We gave a frequency based interpretation of this. Then we came to some important concepts called total probability theorem and Bayes theorem, which helps you to obtain a posteriori probabilities from given a priori probabilities. Okay. I give a problem to solve in the at home, which we can take up in the next class, and then I just introduce you to the concept of statistical independence, which I will try to expand in the next class. So, that is all for today's class. Thank you. Okay. So, in the previous class I gave a small problem for you to work out. So, I am not sure whether you have done it or not, but I would like to spend some time now to solve that problem for your sake. Okay. Let me quickly repeat the problem that I gave. We said that there is a box, there are 4 boxes. Box 1, it consists of 2000 items, out of which 1900 items were good and 100 were defective. Box 2, it had 300 good items, 200 defective items. Box 3, it had 900 good items, 100 defective items, and last box, box 4, it also had 900 good items and 100 defective items. Question that was asked was that, we select any box, any particular box at random first, and then from that box we remove just only one element. The first question is, what is the probability that the particular element which is being removed is a defective one? Okay. So, to answer that, first we see that each of the boxes, since the boxes they are chosen purely at random and there is no particular preference for a special box, maybe box 1, box 2, box 3 or box 4, the probability that I choose box 1, say B1 or B2 or B3 or B4, that is 1 by 4 because it is uniform. That means P B1 is same as P B2 is same as P B3 is same as P B4 is equal to 1 by 4. They are uniform. This is a very safe assumption because there is no preference for a particular box. Okay. And then right across I can write that suppose I choose box 1, then what is the probability that the particular item that is removed from that box is a defective one. Okay, that is P D by less than equal to x. Do you understand the meaning of this? That is, we are now considering all possible events of x for which so that for each of the event the corresponding probability, see we can, for events only we can define probability. So, I am now considering those events for which the corresponding probability is having a value less than or equal to capital X. Okay. That set in short in a compact notation is denoted like this. So, whenever I say random variable x taking values less than equal to x means I am basically considering a set of events, okay, whose probability, I mean maybe since time is up today, I will consider this in the next class in detail. Okay. Basically, just to tell you in a nutshell, I am basically trying to get into what is called probability distribution and probability density functions. Okay. So, in today's class, we started with an example that we gave in the last class. I worked it out. Then we discussed at length the concept of statistical independence. Okay. And then again we highlighted that through an example, and then I went into the discussion of random variables. Okay. I was just getting into the mathematical definition of a random variable. Actually, certain conditions need to be satisfied. This I will take up in the next class. Okay. Thank you very much.